The Zoom meeting is live, so if anybody who's here local wants to join Zoom so you can maybe see these screens better without glare, feel free. Just make sure your mics are muted. If you are part of the online club, make sure your mics are muted, but I may not see a chat or something. It doesn't always pop up on my screen as being very obvious, so just feel free at any point in time to just unmute yourself and ask a question. Just interrupt me, whatever, and I want everybody to feel like they can participate, even the online crew. Sound good?
Yeah, I got a question.
Sure.
So I'm normally supposed to be in person.
Yeah.
I have a little bit of a headache today, so I don't really want to risk it. You make sure they get my attendance down. I don't want you to not see me there.
Yeah, don't worry about it. I get it from online, and I just pretend like I get it from in person.
Okay.
So you'll be fine. I did add, if there was a couple of you last time who showed up and saw the room was fairly full, I added 1, 2, 3, call it 3.5 seats to the back of the room. I have one seat that's just, you'll have to have your laptop on your lap, but it's a nice comfy chair in the very back of the room. So it's kind of a loungy, couchy chair. But I do have an extra 4 seats from last time, although today we have extra seats in the normal audience. So whatever makes you happy, but if you do want to come to class in person and there are not seats available, do let me know, because everybody is entitled to that, and we will figure out a solution. But if you're happy with doing it online, so that the folks that really have a strong opinion about doing it face-to-face can be face-to-face every class, that's appreciated, but it's in no way required. Okay, so let's pick up where we left off last time. Where's my share screen? Oh, there's my share screen. Oh, Indra. Okay. I think that might be the safest place for it. Nobody in the waiting room. Okay. Oh, one other thing I'll mention, I try to pay attention, because when you first join the Zoom, it puts you in a waiting room, unless, I believe, if you're logged into Zoom with your CUW.edu email, then you don't get put in the waiting room. So if you're trying to join Zoom with like a Gmail or as a guest or something like that, that's when you get put into the waiting room. But if you log in with your CUW.edu, you won't have to worry about possibly getting overlooked, because I have to manually click, add to waiting room stuff. But right now there's nobody in the waiting room, but just a heads up for not just my class, but other classes as well. Okay, so last time we were talking about, I'll just bounce forward just a little bit, because we kind of went through some of these slides. We talked about the nature of the CPU. First of all, I kind of talked about it as like this collection of magic tricks, right? Where, we did the little thumb exercise, how many of you are impressed you can do this and do this, but you put these little tiny things together, you can actually accomplish real tasks. And then I kind of skipped over several slides. We're going to talk about these today. But we started talking about the difference between high level, low level, and machine language. So kind of finished off the idea of the CPU a little bit. So human beings like power tools. We want to work with a language that allows us to fairly concisely say a whole bunch of things to the computer. And we looked at the Hello World program in Linux last time more closely, and we saw that even this is a power tool, because it's leveraging the Linux operating system, this special program called syswrite, which requires 3 inputs, which we just loaded into these 3 places. So we're still, with this, leveraging the operating system to do a lot of the work for us. If we didn't have that operating system, we would have had to write the low-level code of all that logic, which might have been hundreds and hundreds of lines of code. All right, so even this, as cryptic as it might look, accomplishes hello world to the screen, is missing a lot of the detail hidden from us by the Linux operating system. And you can replace Linux with Mac or Windows, whatever the target operating system you're working with is. So with that in mind, when we're working with a low-level language, this has a one-to-one relationship with the CPU. So every single line of code we write it's translated into exactly one magic trick on the CPU. But even by today's standards, when a human being writes in low level, we're still getting help from the operating system. We rolled back 50 years, that would not have been the case. We would have been writing all the details ourselves. So we can say that a low-level language is palatable by a human being, but is not necessarily something we'd want to do on a daily basis. High-level language, this is like print hello world in Python, we can handle that. You know, at first you get a little intimidated that, oh, it's code, but you realize it's a whole lot better than these other two guys. Now, machine language, that's the zeros and ones. Now, at the end of the day, what ends up happening is we translate this line into a bunch of zeros and ones. So the move command is a numbered command on the CPU. And we're going to talk about what this means today. So this guy would become a bunch of zeros and ones. This guy would become a bunch of zeros and ones that uniquely identifies this hardware register. This guy would be a bunch of zeros and ones, which is uniquely related to its value, so on and so forth. So this line would become a whole bunch of zeros and ones, which would be decipherable by a human if we sat down and kind of reverse engineered it and tried to figure it out, but it's not something that we can do very quickly on the fly. Okay, it would slow us way down. So we don't want to be operating at that 0 and 1 level, but as computer scientists, we want to appreciate that 0 and 1 level. All right, so let's bounce back then a couple of those slides. And I actually want to go right here. I'm just going to insert a slide. What's a number system? So we all operate typically in decimal, right? What kinds of ideas do we try to share with people with our number system? Okay, values, and what things do we associate those values with? Like, how many fingers am I holding up? 5, right? Yeah, the thumb's the finger. Yeah, so I got 5 fingers. Okay, so we associate a value with responses to stuff. And we happen to use the decimal number system for expressing those values. Now, why do we choose the decimal number system? How come we've kind of stumbled upon that as our default system? You go anywhere in the world and the default numbering system is decimal. Why? What does it mean for our number system to be decimal? Go ahead. Means it's a base 10 number system. What does base 10 number system mean? Or even before we answer that, why do you, oh, go ahead. Okay, almost. It's the language of the base 10 number system is 0 through 9, not 0 through 10. And we've seen this. How many of you remember long division in what, maybe 3rd grade? Something along those lines. So if I said, what is 30 divided by 10? What's the answer of 30 divided by 10? 3, remainder 0? Well, why isn't it 2, remainder 10? Yeah, because 10 goes in another time, right? Now, we can kind of giggle at this and say, well, technically these are the same values, right? 3 remainder 0, 3 with an extra 0 is 3. 2 with an extra 10 is also 3 for the remainder, goes in another time, right? Okay, but we wouldn't write it like this. We would say, oh, well, that's inaccurate because if we're dividing by 10, we can't have a remainder of 10. We can only have a remainder of 0 through 9. Those are our possible remainders when we're dividing by 10. If we had a remainder of 10, that means it went in another time. Make sense? All right. So that's what it means for something to be a base 10 number system, is that we have the language of that number system, the way we express the values in that number system is using a whole bunch of digits, is what we call them, right? So the base 10 number system uses the language of digits to express values, where digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are our digits. Make sense? And as human beings, why did we choose the base 10 number system? Think back in your early days of counting. What did you do? 1, 2, 3, 4, 5. We got 10 fingers, 10 toes. We usually don't use the toes for the counting. Well, maybe, okay? But we picked 10 because it's compatible with us, right? Could we have picked base 8? Is that just as is that just as good of a way of expressing values? Yeah, it's just using a different language, right? Just like in here, we chose to use the English language because that's what I speak. I only speak one language. All right. But if we were in Spain or we were in Mexico, could we be using Spanish? And is that just as effective of a language to express meaning to other human beings? Sure. Natural languages are natural languages. We have all these popular languages and they all get the job done, right? Okay, but we've just chosen English in here. But that's situational on country, right? But number system, we're all human beings, 10 fingers, 10 toes. So we just all decided decimal makes sense. All right, makes some sense? Okay, so the purpose of a number system is to express values in such a way that somebody else can decipher what we mean. And we can actually use a real life example where things get a little bit confusing for us, okay? For many of us, we grew up in the United States, so we operate in miles, right? But when somebody gives you a distance in kilometers, isn't that a little weird for us, right? But if you grew up basically anywhere else in the world, minus like 2 or 3 other places, miles makes no sense to them. Well, actually, they probably figured out miles because they had to figure out how to communicate with Americans. But kilometers are the norm, right? I'm a big golf fan. And so if you're watching golf in the United States, everything is measured in yards. You know, he has 163 yards to the pin. Well, if I'm watching European Tour golf, everything's in meters. I don't know what that means. I mean, I could go and figure it out, but I don't have an immediate idea for the distance in meters. Where we've lived our lives long enough, where if I say 731 in decimal, that has meaning to us, right? We've worked with the base 10 number system enough. Where if I just rattle off some values in the base 13 number system, it wouldn't have meaning to us without us stopping to do the math, even though it's representing the same magnitude, the same value. Okay, make some sense? Okay, so number systems we choose to express value. As human beings, we like decimal. But now we're trying to train ourselves to talk to this guy, talk to our computers, right? Okay. Computers, we don't have the 10 finger, 10 toe thing. So computers are based on digital logic, on and off, 0 and 1. So the base 2 number system, so I probably have some of this stuff duplicated in other slides, but I'll just put it out here as part of my thought process. When we talk about binary, this is the base 2 number system. Why do computers like this? Digital logic, on or off, 0 or 1. Okay, and we've recognized this idea of on or off before. Any of you have at some point in your lives either DirecTV or Dish Network at home, or you've been at a place watching DirecTV or Dish Network? What happens when there's a bad storm outside? No picture, right? You don't get half a picture. You don't get a fuzzy picture. Remember, well, maybe you don't remember. Have any of you ever watched a TV with the rabbit ears? You're getting local channels with an antenna. There's such a thing as getting half a channel, right? Yeah, you know, you could be watching your Brewers game, like, was that the ball or was that snow? You know, so with analog is a wave. It's not on or off. It's a whole sequence of values, okay? So if you're not getting a real great signal, you could have a kind of a fuzzy picture, but you still have a picture. You can still make it out. With digital, which Dish Network, DirecTV, these are digital. Dish Network doesn't even exist anymore. Somebody absorbed them, probably DirecTV, but whatever. I just used that historically since it did exist up to a couple of years ago. With them, they are a digital signal. So you're either getting all the picture or you're getting none of the picture. All right, it's on or off, 0 or 1. That's how computers operate. Things are either on or they are off. All right. Once we get, how many of you have heard the phrase quantum computing? At least in some sci-fi movie at some point or something like that. And it's kind of the, you know, maybe let's say it's going to be the future of computing, but quantum computers add a third level to that. That's not what this class is about. Just figure I'll throw the trivia thing out there. Quantum computers are on or off or spin, where they're called qubits is in a quantum computer. So instead of a digit or instead of these guys are called bits. A bit, the bit language consists of 0 or 1. Those are the bits that make up that language. In the qubit language, the quantum bit language, it's 0, 1, or something called spin, where it's neither a 0 or 1, and it's also both a 0 and a 1. Whole different deal, all right? Don't worry about that for right now, but just kind of more trivia things. That's what quantum computing is. All right, so if we're dealing with the binary number system, this is the base 2 number system as opposed to base 10. Computers like this because they are digital logic. The language, you can think of them as having 2 fingers, 2 toes, if you want to kind of think of them like humans, right? The way they count, they only have 2 different choices, on or off. And actually, it's not even 2 fingers, 2 fingers, 2 toes. It's 1 finger that can either hold up or not hold up, right? So on or off. So the language that we use to express binary numbers uses 0 and 1. That's the vocabulary of that, and they're called bits. We're speaking English, we could be speaking Spanish, we could be speaking French. In this case, we have the English alphabet, right? Then we have the Spanish alphabet, you have the French alphabet, so on and so forth. This guy here is the alphabet of decimal numbers. This guy here is the alphabet of binary numbers. All binary numbers are made up of those letters, that alphabet. Make sense? Now, other popular bases, and I'm going to kind of give you the punchline in a little bit, maybe next class actually, but that we run into with computers is something called hexadecimal. Anybody know what base hexadecimal is? So decimal is base 10, binary is base 2. What base is hexadecimal? Nope. 16. So base 16. Why do we use it? I'll just put a couple dots there for right now. We'll get to that, the punchline, but I haven't given you enough information to tell you why it's popular yet. All right. Now the alphabet for the hexadecimal, these are called hextets. Okay. Now the reality is most humans will just call them, oh, the digits we use are 0 through 9 for decimal. The digits we use are 0 through 1 for binary. most of us will just say it like that, but technically the alphabet, it has names. So it's the digits for base 10, the bits for base 2, the hextets for base 16. Okay, so the alphabet for base 16 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then A, B, C, D, E, and F. And you can think of this as 10, 11, 12, 13, 14, 15. So to kind of go along with our, if it's base 10, it's 0 through 9. If it's base 2, it's 0 through 1. If it's base 16, it's 0 through 15. So it's 0 through the base minus 1 is the language, the alphabet of that language. But each hextet, each digit, each bit has to be exactly 1 character long. Hence, we use an A to represent a 10 rather than 1, 0. Because if we use 1, 0, now it becomes ambiguous within the numbering system because we're now using 2 different characters to represent 1 value. And how do we know that that's 1 value versus 2 values? Make sense? Okay, so we always have to use a single character for representing a value. So that's why after we hit 9, once we get to the double characters, we use A's and B's and C's, so on and so forth, up to an F. If we were dealing with base 18, we would have G and H added on there. Make sense? All right. But I'm introducing the popular numbering things when we're dealing with computers. You could have any base between base 0 and base 37 because we have 26 characters in the English alphabet. Yes, we've tried other languages like Klingon. Actually, the Klingon alphabet only has 22 characters in it. I assume that was your question. No, it wasn't. Okay. Go ahead. Not kidding, by the way. We did look into Klingon. Well, let's say officially, no. Officially, upper and lower case are, let's say, used interchangeably, but I would say traditionally it's always uppercase. But, and this will connect to maybe some of you, if trying to think of the name of the game, and there's like 50 or 60 different like versions of it. I think it's something called like, it's a mobile game called like Tap. You're like a guy who sits there and he like beats up some monster and it starts rattling off giant numbers where you're collecting coins or something like that. It's like Tap RPG or something. But what's interesting about it, I'll figure out the name of it. I've had it on my phone before. It's kind of fun, and then you figure out a way to hack it. But you know, in any case, they use a crazy numbering system because as you get to like, you know, level 5,000 and stuff like that, you know, every single time you hit them, you're hitting them for a ridiculous amount of damage. So it's spawning off coins. And the way they're representing that numbering system is they even get into like double, triple letters in the alphabet. So like you might have a single value being AAA. So they kind of break the rules of the single digit thing. But this kind of goes back to the idea of all we're doing here is we're picking a language to represent a value. So if we're choosing to use the English language as our baseline for representing numeric values, we are stuck with 0 through 9 and then the English alphabet, A through Z. Now we can kind of toss in there, maybe we can set a rule and say, well, after we use the uppercase letters, we use the lowercase letters. So then we expand the numbers we can represent if we do differentiate between upper and lowercase, but it's not part of the official standard. More so that we, as human beings, we don't really need to represent values that large conveniently. We don't have to conveniently represent values that large. If we're working with numbers that are that big in magnitude, we just do the whole decimal thing and make it look really impressive. If you've ever seen the, you know, the biggest number they've calculated, the biggest number of significant digits for pi, they've calculated, they actually printed it out. It's like this giant volume of pages that is like that high. You know, it's just got numbers on it, you know, for 3.14, 159, blah, 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 so on and so forth.
And Mr. Libin.
Yep, go ahead.
Kevin told me to tell you that he's in the waiting room. He wants to know if you can let him in.
Nope.
All right.
Yeah, I'll get him in.
All right.
All right, there you go. And there was another example there. You see it showed up as guest. If you sign in as your CUW account, you'll never get dumped into a waiting room. At least I don't think you will. You'll automatically be able to get in there. But if you join the room as a guest, then it'll you'll get tossed or at least put on hold. All right. So we're kind of getting the idea here. We're using a language to represent numeric values. And we just happen to have some different kinds of numeric values that we use. So hexadecimal uses the idea of, well, it's base 16, whatever that, however that helps us, we'll kind of get there. That's where the why do we use it part. But the language of that is called the hextet language, and it's 0 through 9, A through F. All right, another popular, I'll just actually steal this slide. Did I get two of them? No, I have two of them. We have the octal number system. Want to guess on what base that one is? Base 8. And these guys are called octets. And this is 0 through 7. So 0 through, oh, that was what the last thing I had copied apparently. So that was 0 through, let me get that off of this slide. 0 through 7, or 0 through the base minus 1. All right, makes some sense? All right, so now what's the number system that we're most familiar with? It's decimal, right? So we all know everything there is to know about decimal numbers, super comfortable with it? All right, so remember when this kind of was going to prove a point to us, I think. So I said one of the reasons that computer programming is hard is because human beings are such good problem solvers that we have trouble articulating how we solve problems. And I think we're going to see something fairly similar here with decimal numbers. So we'll just come here. So let's say we have the number 127 in decimal. What does that number mean? We're using that to represent a numeric value. What does the numeric value 127 mean? Is it 127 digits? Go ahead. It would be if we were dealing with base 1. 12 tens and the 7, and so 7 ones, going off your logic? 12 tens and 7 ones. Okay, that would be kind of equivalent to earlier where we said 2 remainder 10. So so I'll say what you just said is not correct, but can be translated accurately. So you're about
12 tens and 1 7.
Yep. So this is 1 by 100s. This is 2 by 10s. And this is 7 by 1s. So this 7 here is in the 1s place. This 2 is in the 10s place. This 1 is in the 100s place. So 1 times 100 equals what? 100. 2 times 10 is equal to what? 20. 7 times 1 is equal to what? 7. You add those three numbers together, 100 plus 20 plus 27 gets you what? 127. We just converted the decimal number 127 into the decimal number 127, which somewhat of a waste of time, but also is mathematically correct. We just saw it happen, right? All right. So now, actually, I'll steal this slide. First of all, Is this a legal octal number? I'm telling you that number's an octal. Is that a legal octal number? What makes a number legal in octal? No, in fact, that's not divisible by 8. Go back to our octal slide. Octal numbers are made up of the language of octets, right? Only 0 through 7. Is this number made up of only 0s through 7s? Yep, so it's legal. I had to, but this is also a legal decimal number. It's also a legal base 9 number. It's also a legal base 13 number, which we didn't give a name to, but it's a legal one of those. So I do have to tell you what base it's in. So when I say this is 127 in octal, octal is like a common term for base 8. But if this was base 13, there probably is an official name for base 13. It's just not a common one. I would probably say this is 127 or 127 in base 13. Okay? But we just decided that this is a legal octal number because it's made up of the octets 0 through 7. I don't use any octets outside. I don't use any digits or characters outside of that alphabet. Make sense? Okay. So the question is then what does this, if I want to convert this number to decimal, because we understand decimal, we want to kind of know what that number means. When somebody says 127 in octal, what does that actually mean for us? That's like somebody giving me a distance in kilometers, and I have to go Google how far it is in miles, something like that, to get an idea of what that means, because 127 kilometers doesn't mean that much to me. Make sense? You know, or if somebody gives you, then, you know, we all have that line, right? If somebody gives you something and, you know, it's 127 trillion, blah, 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 you know, millimeters or something like that. You know, we don't have an idea of what that really ultimately means. So I'm going to say, well, I understand the world of decimal, so it would be beneficial for me to convert this 127 octal number into a base that means something to me. So I'm going to start over here on the right side. We always start the right side. This is the ones place. So 1, I'm just going to put some spaces in here, 2, 7. I'm going to write it out here and then I'll explain what it is. So the far right value is in the ones place. Just like when we were talking about this number, you told me there was 7 ones, right? So it's always the ones place. I'll actually write it in even a more formal way here. This is 8 to the 2's place, 8 to the 1's place, 8 to the 0's place. 8 to the 0th power is 1. 10 to the 0th power is 1. 2 to the 0th power is 1. That's why the far right value in any numeric number is always in the ones place. All right. And then as I move to the left, I multiply it by the base. So to go from, I'm in the ones place, times 8 is the 8's place. Times 8 is the 64's place. Times 8 is what, 256? 64 times 8, 512's place. So on and so forth. Times 8 is 4096, I think. All right, so what do I do with this? I take 7 times 1. I add to it 2 times 8. I add to that 1 times 64. And that gives me the number 87. So 127 in octal is equivalent to 87 in decimal. Those are both the same value. just represented using two different languages. Make some sense? So really think of this as like this idea of miles versus kilometers, meters versus yards, that kind of stuff, okay? Computers like the binary, they also like octal and hexadecimal, and I'll explain why soon. That's a punchline we'll hold out for a little bit. But in general, these are all different numeric bases that all represent the same magnitudes using a different language. Okay? So if I take my favorite hexadecimal number, bad, from hexadecimal to decimal, so we have B, we have A, we have D. This is the .256 place, 16's place, 1's place. But B, A, and D, these actually represent larger values, don't they? B is an 11. A is a 10. D is a 13. So this is 13 times 1 plus 10 times 16 plus 11 times 256. Which is 2989. See how that's working? 1's place times 16 is the 16's place times 16 is the 256 place. As I keep going left, times 16 is the 4096 place, so on and so forth. So we've learned a single pattern that can convert from any base, including base 10, right? We saw base 10. I went from 127 in decimal to 127 in decimal. It worked. Waste of time, but it did work. That same identical pattern. If this was decimal, this is the 1's place times 10 is the 10's place times 10 is the 100's place, so on and so forth. All right, so same pattern lets me go from any base to decimal. Questions about that math? All right, so let's test you then. I don't want to go too deep in the alphabet either. I don't have to count too. We'll just leave it at this. In base 14 to decimal. So convert 1AB2 from base 14 to decimal. Give you a couple of minutes to take a stab at that. You got an answer? All right, give me a second. I got about 20 more seconds and then we'll go through it. All right. So what do you, Ben, what do you think the answer is? 4,860. That's our calculated suggested answer. So let's go through this. So we're going to say we have 1, A, B, 2. I'm going to rewrite this as 1, 10, 11, 2. This is the 1's place, the 14's place. 14 times 14 is the 196 place. Times 14 is the 2744's place. This is 2744. This is 196. This is 14's. This is the 1's. So we have 2 times 1 plus 11 times 14 plus 10 times 196 plus 1 times 2744. $48.60. Yep. So this equals 48.60 in decimal. All right. Questions about any of that?
Yeah, how do you do the bottom part? Like, how'd you get 196 and 14?
So this is always the 1's place. So this is 14 to the 0th place, 14 to the 1st power, 14 to the 2nd power, 14 to the 3rd power. Just like if we were dealing with a decimal number, like we had 127, this is the 1's place, the 10's place, the 100's place. 1 times 10 is 10, times 10 is 100. So since we're dealing with base 14 here, this is always the 1's place on the far right, times 14 is the 14's place, times 14 is the 196 place, times 14 is the 2744's place. If this was base 16, this would be 1 times 16 is the 16's place, times 16 is the 16 times 16 is the 256 place, times 16 is the 4096 place. Does that make sense? Assume maybe. Okay. So that's how we always get these bottom values. This is always 1, always, always, always. Because it's always whatever the base is to the 0th power. It's always 1. And then as we move to the left, we multiply it by the base, times 14, times 14, times 14. All right, other questions on this? Okay, so we're comfortable. We can convert from any base between base 1 and base 37 to base 10 to decimal using this identical pattern, right? Okay, so we had to learn one pattern. Now we can go from any base, including decimal, back to decimal. What if we're looking at going the other direction? So, and just actually, let me just throw one more example in here because it's the one most pertinent to computers. So if I have 101101, for example, from base 2, so from binary to decimal, go ahead and take about 2 minutes and solve that one. 1011101. All right, so let's walk through this one. So we have 1, 0, 1, 1, 1, 0, 1. This is the ones place, the twos, the fours, the eights, the 16s, the 32s, the 64. So this is 64, 32, 16, 8, 4, 2, and 1. Now, one nice thing we can do with binary is anytime we have a 0, we actually don't even need to do the math on it. I'll still put it in here so you can see the identical thing, but 0 times anything is always 0. All right, so this will be 1 times 1 plus 0 times 2 plus 1 times 4 plus 1 times 8 plus 1 times 16. We also see the 1 times anything is always the anything. So plus 0 times 32 plus 1 times 64. 93. So this guy right here is the decimal number 93. All right, make sense? All right, so now let's go the other direction. What if I have a decimal number and I want to get it into another base? So I say, oh, I have the number 93, but I want to figure out how to represent it in binary. So let's just reverse this one. So we'll say 93 in decimal to binary. Okay, so we're going to learn a second pattern now. How do we go backwards from another base, or I'm sorry, from decimal to another base? All right. Now, we kind of already mentioned this once, but if you remember 3rd grade math, we had long division. Remember how much you loved long division? How many of you distinctly remember not liking long division? I remember not liking long division. I think I was maybe too busy. I think I was eating gum at that age. I don't remember. I remember, and this is back years and years ago, they used to still spank kids in school. I got spanked 3 times in 1st grade. Each time, well, 2 of the times was for eating crayons. I was a big fan of that food, I guess. I'm not even sure if back then they were safe. I don't know what they were making them out of, but man, what are you gonna do? But I'm just saying long division might not have been a high priority for me at that particular age. So in any case, when you do long division, if I say, for instance, 93 divided by, I don't know, let's do 7 or something like that. You know, you say, how many times does 7 go into, and then you end up getting your answer with a remainder, okay? So that remainder in modern day logic is actually really, really important. It's called modulo. So if we take 93 divided by 4, for example, 93 divided by 4, we get a 23, okay? 23.25 if we're doing floating point math. But if we're doing integer math, this gives us a 23. 93 mod 4. So if I take 23, multiply it by 4, I get 92. I have a remainder of 1 that gets me to the 93. So this guy is 1. So this is integer division if both things are ints on either side. And that's true in programming languages, and we'll talk about that. Actually, in Python, just so I can, even though we're not talking about this yet, if you want to force integer division, you actually have to use a double slash in Python to force integer division. I'll mention that again. I just, in context here, I'll say it this way. Most modern programming languages will say if the left side is an integer and the right side is an integer, I will treat this guy as integer division. But if one of the two sides is a decimal number, then I'll treat it as floating point division. Go ahead.
You can also put in parentheses for it to represent it as a unit.
Well, you can do something like this. You can typecast the answer here in some languages. Yeah, but don't worry about that for right now. Okay. Point we're getting across here is that there are two halves to integer division. There is the division part of it, which gives you a quotient. Okay, so this is 93 divided by 4 will give me the whole number part, the 23. 93 mod 4, modulo 4 is, that's the symbol typically for modulo. In some languages, it's just mod, like that. But 93 mod 4 will give me the remainder of 93 divided by 4. And the way you can calculate this is you can say this number times this number will give you something, and then take this number and subtract that from it. So 23 times 4 gives me a 92. 93 minus 92 is a 1. That's what's left over, my remainder. Okay, so this guy gives me the remainder of that integer division. Let me just steal this. I'll throw it on a... It's called modulo. All right, make some sense? Okay, because we're going to be using that division and that remainder for this pattern of going from a decimal number to a base. So if I want to go 93 to binary, I'm going to start off at 93. I'm going to continually divide it by 2 and record the quotient. So 93 divided by 2 is 46. 46 times 2 is 92. So I have a remainder of 1. So I record my remainder out here to the side. 46 divided by 2 is 23. 23 times 2 is 46 with a remainder of 0. 23 divided by 2 is an 11. 11 times 2 is 22 with a remainder of 1 to get me to 23. 11 divided by 2 is 5. 5 times 2 is 10 with a remainder of 1 to get me to 11. 5 divided by 2 is 2. 2 times 2 is 4 with a remainder of 1 to get me to 5. 2 divided by 2 is 1. 1 times 2 is 2 with a remainder of 0 to get me to 2. 1 divided by 2. How many times does 2 go into 1? 0 times. Doesn't go into 1. 0 times 2 is 0 with a remainder of 1. We know we are done when we have a 0 right here. We've completed the algorithm for converting a decimal number to a, in this case, a binary number. We read our answer from bottom up. This is actually really funny. It seems like every single semester when I pick my example, I happen to pick example that reads the same from bottom up and top down, okay? We are doing it from the bottom up here. So this is a 1, 0, 1, 1, 1, 0, 1. 1, 0, 1, 1, 1, 0, 1. I should have known that from the previous slide, but it didn't occur to me I would have that bad of luck.
So you're just divide by whatever the base is?
Yep.
I have a question.
Sure. Go ahead.
So when like right before you started doing this, I was like thinking of like how I do it myself, and I was thinking, since we're in like binary, I was thinking of like what's the biggest like number in binary that would go into 93. So I was thinking like 64, and then see that it goes into it once, and then doing it that way. How like inefficient would that be in the long run?
Well, it's not so much inefficient as much as it is, it's not a universal algorithm. So,
Okay, yeah,
so,
I understand.
yeah, you could accomplish that in binary just because it's doable, but you can apply this algorithm to every single decimal to any base conversion.
Okay.
I would probably say this is probably less error filled as well. You know, just because it's kind of a paint by number, you're whittling it down till you get to your 0. But what you said you're doing is not something that's uncommon. So once you're used to working with binary numbers and something like that, I mean, you're probably going to just glance at a number. You're going to say, oh, well, what's the number 5 in binary? Well, you just kind of figure that out real quick. You don't go through this whole process of dividing and recording remainders. But there does become a point where you're like, you know, so what you're saying is figure out the largest power of 2 that's less than your number. 64 is less than it, 128 is greater than it, so I'm going to have a 1 in the 64's place. You know, then you count down from there. You can certainly accomplish it that way. Good. Yep, and we're going to do some more examples. So we should be able to check our work here. This was 1011101, and we got that same answer wherever I wrote it, right here. Let's go back and we'll undo one of our base 8s. So we have an 87 in decimal. We want to take this to base 8. We're expecting a 127 out of this guy. So 87 in decimal to octal. Go ahead and take a couple minutes and give that one a shot. I know I've only gone through the algorithm once, but let you stew on it for a second, then I'll do it. But as you asked, instead of dividing by 2, we're now dividing by 8. Possible remainders are 0 to 7. We're dividing by 2, possible remainders were 0 to 1. All right, so let's go through this. So we'll take 87, we divide it by 8. 87 divided by 8 gives me a 10. 10 times 8 is 80, with the remainder 7 to get to 87. 10 divided by 8 is 1. 1 times 8 is 8, with a remainder of 2 to get me to a 10. 1 divided by 8, how many times does 8 go into 1? It goes in 0 times. 0 times 8 is 0, with a remainder of 1 to get me to 1. We know we're done when we hit a 0 here. We read our answer from bottom up, 1 to 7. In octal. Make sense? All right. 2989 decimal to hexadecimal. base 16 as a reminder. So go ahead and take a couple minutes and give that one a shot. All right, so let's go through this. 2989, we're going to divide this by 16. 2989 divided by 16 gives me a 186. 186 times 16 is 2976, so that's a remainder of 13. 186 divided by 16 is 11. 11 times 16 is 171. Oh, 176. So that's a remainder of 10. 11 divided by 16. 16 goes into 11 0 times. 0 times 16 is 0. It's a remainder of 11. We know we're done. We read our answer from bottom up. So that's an 11, a 10, and a 13, or translated, a BAD. Because we need to take the 11 and convert it into the appropriate hextet, the 10 and convert it to the appropriate hextet, and the 13 and convert it to the appropriate hextet. Make sense? Okay, so now we know how to convert from any base to decimal and from decimal to any base using two patterns. And we understand that the purpose of having numbers in different bases is being able to explain to different people value, right? Human beings like decimal, computers like binary. Now, I mentioned earlier, they also like hexadecimal and octal. And let's talk about why. Let's say I gave you that number That'll be good. And I say go from binary to hex. So this number from binary to hexadecimal. Go ahead and take a couple minutes to do it. What would you do? You'd go from binary to decimal first, and then convert the decimal into hexadecimal. You're gonna have to apply both of our patterns, right? So first turn this number into decimal, then take that answer and convert it into hexadecimal. And then I'll show you the shortcut. So we're gonna do pattern 1 first, and then pattern 2, the one we just covered, to get our final answer. I'm going to start typing a few things just for the sake of time here, so you can keep working for a second. All right, so let's go through this. So I exploded out this binary number. So this is 1 plus, we don't need to do the 2 times 0, 4 plus 8 plus 16 plus 64 plus 128 plus 512. So 733. I look right for the first part. And then you take 733 and you divide it by 16 over and over again until you get the hexadecimal number. We only have a minute left, so let me just show you the trick. We can take this number, we can divide it into packs of 4, because the entire hexadecimal set can be done in 4 digits. 0, 0, 0, 0 is 0. 1, 1, 1, 1 is 15. Covers the entire hextet value. So this guy right here is 1 in the ones place, 0 in the twos, 1 in the fours, 1 in the eights. So this is 13. This is also a 13. And then there's like an imaginary 2 zeros before that guy. So this is a 2. So this is 2 DD. Should be your final answer. So I took my binary number and I split it up in groups of 4 starting at the right-hand side, and then converted each of those into their hexadecimal equivalent. Make sense? And this gives me, so you didn't have to do all this math here in order for this to work. All you did is took your binary number, split it into packs of 4, convert each pack of 4 into its hextet, and then, the 13s become Ds. So one of the reasons why hexadecimal is popular is you can very easily move between hexadecimal and binary. The same thing is true for octal, since all of the octets can be represented in 3 bits, 0 through 7. 0, 0, 0 is 0, 1, 1, 1 is 7. So you can do the identical trick with octal. Okay, I'll start off class on Thursday reviewing this. We'll do an octal one as well. But that's the reason why they are popular, is because how conveniently you can move between binary, hex, and octal. It would not work for base 11, because you don't cover the entire language set in a certain number of bits. All right, I will see everybody on Thursday. I think we're coming up on our first assignment. So I'll finish up this stuff, and then we'll have our first assignment after that. All right, well, our first real assignment. You had Bible homework due on Sunday. All right, I will see everybody on Thursday. Any questions from online before I sign off?